Hello everyone. Welcome to this lecture on these four topics: energy bands, holes, effective mass and Fermi level. We have seen earlier that materials could be classified based on their conductivity as metals, semiconductors and insulators. Solids can also be classified as crystals, polycrystalline materials or amorphous based on the way its atoms are arranged. In a crystal, we have a long range order throughout the three-dimensional material. The amorphous, on the other hand, is at the other end of the spectrum. It would be difficult to find any order even at very short dimensions. Polycrystalline materials lie between crystalline materials and amorphous materials. They are composed of grains where each grain has a different orientation and each grain looks like a small crystal. In order to make an IC or a semiconductor device, we require all three materials. For example, this is a high resolution TEM of a gate, the gates on the of a gate stack of a MOS transistor. So here the substrate you can see is made of crystalline silicon. So you can see atoms arranged in a regular order. The gate on the other hand is made of polycrystalline silicon. So here you can see one grain, here you can see another grain, here you can see another grain. Right? So they are all of with a different orientation. There is an insulator between the polysilicon gate and the crystalline substrate, right, which is made of silicon dioxide, which is an amorphous material. So even though the thickness of this amorphous layer is only 20 angstrom, it is very difficult to find any order in this amorphous layer. The growth and the deposition conditions determine whether a material finally becomes crystalline, polycrystalline, or amorphous. Silicon can be made in all three forms. Here is a unit cell of silicon crystal lattice. If you take this unit cell and repeat this cell in all three dimensions, one gets the full silicon crystal lattice. Since we know that if we have a quantity which is periodic in real space, right, we can construct something known as a reciprocal lattice. So the reciprocal lattice, it can be thought of as a Fourier transform of a lattice in real space. This is analogous to Fourier transform in signals and systems, where the variables are time and frequency. So for any point G in the reciprocal lattice, right? So this relationship should hold true for all the points R in the real lattice. If you know the basis vectors of the lattice in a real space, right, one can use them to create the basis vectors of a reciprocal lattice. So you may be wondering why we are using reciprocal lattice, right? So that is because the reciprocal space is used to understand material properties which are not obvious, right, by only looking at the properties in real space. So one of the first tasks in a semiconductor course or solid state device course is to calculate the electron concentration at equilibrium. So in order to calculate the electron concentration at equilibrium, we should know first how the electron energies are distributed inside the material. So we now know that electrons are quantum mechanical particles. So we need to take the help of Schrodinger's equation. So here we have the time independent Schrodinger equation. Let us first try to solve this equation for a simple case, that is for a free particle. Okay, free particle means it doesn't encounter any potential at all. So the solution for this equation is that of a plane wave. That wave or a particle, right, it can take any energy on a continuum level. So we can construct an EK plot, which is also known as the dispersion relation, right, where E is the energy, K is a wave vector or wave number, right. For a free particle, it takes the form of E is equal to h cut square k square by 2m, right. So this is equivalent to E is equal to p square by 2m, right, where p is the momenta, right. So in quantum mechanics or in crystals, we will see later that momentum can be written as h cut k. So this EK relationship for a free particle, it has a form of a parabola. Now let us take the case of a electron which is bound inside a potential well. So the potential well could be infinite or finite, right? So we typically see the example of an infinite potential well because that gives you closed form solutions. So we encounter finite potential well in the case of an isolated atom, or a quantum well, or a nanowire. So in this nanostructures, the electrons could be confined in one or more directions. So if you try to solve the Schrodinger equation for such cases, the eigenvalues or the eigenstates are no longer continuous as the case of a free particle. So in such cases, the electron eigenvalues or the electron energies, they are discrete, they're quantized, right? So for example, for this potential well, the electron can take only these energy levels. So both energy as well as momenta or the wave number, they are quantized for an electron which is there in the infinite or finite potential well. Now let us move forward and take the case of an electron, right, which is there. Let's take the case of an infinite crystal, right, where the atoms are arranged in a regular lattice. So here a free electron, okay, it sees something as a periodic potential well, right? So the potential well, they are Coulombic in nature, right? It goes down where there is a core, right? Near the nuclear core, it goes down nuclei, and it goes up again. So you can see actually in a three-dimensional solid, okay. So you can see this is a three-dimensional periodic potential well, right? So this is a difficult problem to solve, especially if you are trying to solve using pen and paper. So in around 1930, two gentlemen, Kronig and Penny, they solved this problem for a one-dimensional lattice. So in order to solve this problem, they approximated this Coulombic potential well as rectangular potential wells, right? So then it is easier to solve. So this derivation is given in all introductory quantum mechanics and solid state physics books, some of which are given as a reference here at the end of this lecture. The solution for Schrodinger equation in this case, okay, it gives discrete energy bands, right? So you can see this is one band, second band, third band, fourth band, like that. And these bands, okay, so in these bands, electrons are free to move. They can move as if it is like a free particle. But between these bands, okay, there are forbidden gaps where the electron energies are not allowed. So in reality, there are many such bands and gaps. The width of this band and the exact location where a band occurs or where a gap begins, okay, it depends upon the way the atoms are arranged in the crystal lattice. These bands and gaps, it can be seen in the real space as well as in the reciprocal space. So the main message here is that so energy bands and gaps, they arise automatically in crystalline solids, right, where the atoms are arranged in a periodic manner, where the electron sees a periodic potential well, right? So when you solve Schrodinger equation for a case, the energy bands and gaps automatically arises. So similar to a signal, right, periodic signal, which can be represented in time and frequency domain. So we can have this electron energy spectrum. It can be also represented in real space as well as in reciprocal space. So there are two such representations. Okay, one is known as an EX, right? Electron, the spectrum we plot against the real X variable, okay, which is the variable of a real space. So such a diagram is called as energy band diagram. And if you plot the energy versus k vector or the wave number, okay, that is known as a band structure. So if you have a homogeneous three-dimensional crystalline solid, right, then the EX diagram, okay, for an example, in the case of silicon, it looks like something like this one, right? So you have the conduction band. The width of the conduction band is around 4 electron volt. You have the energy gap, which exists between the conduction band and the valence band. Then you have a valence band. Okay, the width of the valence band is 12 electron volt. Okay, then there is another band gap below this valence band. Okay, so this is if you try to plot the EX diagram in any direction of a three-dimensional material, okay, it looks like this. It looks similar. However, the EK diagram, okay, it gives more detail. So from here you can see this energy versus k, it depends upon the direction you take in the reciprocal space. For example, these notations L, lambda, gamma, delta, these are standard notations. Okay, so these are the positions inside a Brillouin zone. Right, so Brillouin zone is something just like earlier we saw the unit cell of silicon in the real space lattice. The similarly Brillouin zone, or the first Brillouin zone, that is the primitive unit cell in the reciprocal space. So if you replicate the first Brillouin zone, you can span the entire reciprocal space. So these points and the direction, those are the various directions and the points of symmetry in the first Brillouin zone. So you can see along the, so for example, if I go from gamma to x, that is from gamma to x, okay, this is how the band diagram looks like. This is a conduction band, it moves like this one. The valence band moves like this one. Okay, so similarly for other directions. So you can see in the EX diagram, the bottom of the conduction band was flat, right? However, if you look at the EK diagram, the bottom of the conduction band goes like this one, right? So, and similarly, the top of the valence band is flat in an EX diagram. However, if you look at the top of the valence band, it goes like this one, right? So this is the EK diagram for silicon. If you look at the conduction band, it has got a minima, right? So this is not evident from the EX diagram. So you can see the conduction band minima occurs here, and similarly, valence band maxima, it occurs here, right? So these are some additional information you can get only from the band structure rather than the band diagram. So we saw the one of the consequence of this one from one of the earlier introductory lectures, that you can, the silicon, okay, so only this EK diagram, it can explain why silicon is not an efficient light emitter. That is because the conduction band minima and the valence band maxima, they occur at a different k vector. So here also you can see the valence band is around 12 electron volt, and below the valence band, this shaded region, this is the band gap below the valence band. However, the EX diagram, okay, it becomes useful, okay, when there is an irregularity in, or when the regularity is broken of a three-dimensional homogeneous crystal. Okay, so the various ways by which we can break that homogeneity is by introducing doping or introducing new materials, right, or make the dimensions very small, right? Or another case is you apply an electric field. Okay, so all these cases happens in semiconductor devices. So that is why we typically draw the energy band diagram for semiconductor devices. So having learned about the energy bands, now let us see how these bands are populated by electrons. As we saw before, right, there are many such bands, right? So in the case of metals or semi-metals, okay, the one band, the top band is partially filled, or there could be an overlap between two bands. However, in the case of semiconductor or insulators, there is a clear demarcation between completely filled bands. These are the completely filled bands, and these are the completely empty bands. So this is a case at 0 Kelvin. So among these bands, the topmost filled band. So in this case, in this picture, there are two completely filled bands. So I take the topmost filled band. Okay, in this case, this is a band 2, right? So we call that band as the valence band. The band above the valence band, that is this band, right? That is called as the conduction band. So here the band 3 is a conduction band 2 is a valence band. So if you raise the temperature, what happens is that some of these electrons which are there in the valence band, they can gain energy and they can end up in conduction band. So now let us see how can we calculate current, right? Current due to the carriers. For a completely filled band, okay, for a completely filled band, the states doesn't contribute to any current. They don't contribute to any current. That is because this EK diagram, this is actually symmetric, right? So for a completely filled band, for every wave number, for example, let's take this electron with this wave number, right? There is an identical state on the left side, right, with an identical k vector, right, and with a negative slope. So you can see this. So the velocity or the group velocity of the particle is defined by the slope of the EK diagram. So slope of the EK diagram. So for this electron may have a positive velocity, this electron may have a negative velocity. So this, if you sum up all the velocities, the net current is zero. So this is true in the case of conduction band also, even though it's not completely filled, the electron distribution is symmetric across the K at equilibrium. So that is why the current due to electrons in the conduction band is also zero at room temperature. Now let us see what happens when an electric field is applied to the system. So this is a case of a zero field from this, again from the previous slide. Okay, this is a zero field. Now what we have done is that we have omitted the completely filled band and completely empty bands. Okay, so we need to only focus on only these two bands. This is a conduction band and this is the valence band. So if you apply an electric field, let's assume we are applying an electric field in the positive x direction, right? Then what happens is, suppose let's take the case of the electrons in the conduction band. So these electrons, okay, since the field is in this direction, the positive x direction, okay, there is an applied force. The force is on the negative x direction, right? So they will grow over time. They will grow. Their velocity becomes negative, right? So how do you show this? So that the distribution of these electrons, okay, what happens is that they shift to the left arm of the EK diagram, right? The reason why is that the left arm of the EK diagram, the velocity is negative, right? So here is a question to ponder, right? Why there are still electrons in the right arm of the EK diagram with positive velocity? So you can also try to calculate how a redistribution happens for the valence band electrons. Okay, this is left as an exercise for you. Let us now calculate the current due to these valence band electrons. It can be written as the current due to all the electrons in all the k states, right? Then you subtract those k states which are empty, right? So this current density, it is it's given by the charge multiplied by the group velocity of the particle. Then you sum up, then you finally divide by the volume. The first term here, it actually gives zero because we are calculating the current from all the states, right? So this is zero as we have seen earlier. So you can see here there are two negative signs, right? These two negative signs make the sign of the result positive as here. So the conclusion is that one can obtain the same current if we keep track of only the vacant states, right? But assign them a positive charge. So when we apply an electric field or a magnetic field, one can either write dynamical equations and get the results by tracking large number of valence band electrons with negative charge, or you can get the identical results by tracking small number of vacant states with positive charge. So this is the concept of holes, which was introduced by Rudolf Peierls in 1928. Now let us look at another important approximation, the effective mass of a particle. So we have seen earlier that the group velocity of a particle is related to the first derivative of EK diagram, EK plot. So we also have seen momentum of a particle can be written as h cut into k. So if you equate the derivative of both these quantities, that is essentially you are trying to equate the force. It's like force equal to ma, right? So you can write force is equal to dp by dt is equal to h dk by dt. On the other side, you can write forces m into acceleration. Acceleration is nothing but d vg by dt. So if you get these two expressions, okay, if you do a little algebra, you can get a quantity which is identical to something known as which has a dimension of mass, right? So we call that quantity as the effective mass, right? So if you do the algebra, you can derive the expression for the inverse of effective mass is like 1 by h cut square dou E square by dou k square, right? So this term is actually nothing but the curvature of the EK diagram. So let's take a simple case of an energy band diagram, right? So we know that at this is take any representative band. So this is the bottom of a band and this is the top of a band, right? If you try to calculate the curvature of this band, right? So this curvature is always positive at the bottom of the band. right? So then we can say the effective mass is positive at the bottom of the or of all the bands. Similarly, the curvature becomes negative at the top of the band, right? So that means the effective mass also becomes negative. All right. So the effective mass is shown here. Okay. So near the bottom of the band, the effective mass is positive, right? Then what happens? It slowly increases. Okay. Slowly increases. Then sometime somewhere in between the curvature changes sign. Okay. So then what happens is the effective mass also changes the sign. Finally, it becomes negative. Okay. It becomes negative at the top of the band. So that means, right? So we know that the electrons, okay, so that means the electrons at the bottom of the conduction band, okay, they have positive effective mass. Similarly, the electrons at the top of the valence band, they have negative effective mass. So the band structure of a material or the band structure effective mass of a material actually it depends upon three factors. One is it's a material, right? Different materials have different curvature at the bottom of the conduction band and similarly at the top of the valence band. So hence the effective mass of electrons and holes in silicon, germanium and gallium arsenide, they are indeed different, right? So for example, if you take if you look at this EK diagram, okay, so the EK diagram, this has got a different curvature compared to this material, right? So that will result in a different effective mass. So this material has got a slightly higher effective mass compared to this material. The second factor is energy, right? So energy. So as you can see here, as you go higher in energy, what happens is that okay. So as you go higher in energy, there's a change in the curvature, right? And as you go higher, okay, there's the sign of the effective mass also changes, right? So from bottom to the top, okay, the effective mass goes from positive to negative. The third factor, which is that it depends upon the direction of propagation or the crystal orientation. That is because the EK diagram we saw earlier that it is different along different directions of the reciprocal space. So the effective mass finally depends upon the crystal orientation. So in reality, effective mass is actually a tensor quantity, right? Which has to be represented by, okay, this is the inverse of effective mass tensor. Okay, it has to be represented by 9 components, right? That means, okay, this is a relation between acceleration and the force, right? So that means if you apply an electric field or something, right, the acceleration felt by the charge and the direction of the electric field, okay, it need not be collinear. They need not be in the same direction. So you may be wondering why we are doing all this, right? So this actually enables, right, us to treat electrons and holes in a solid semi-classically if we replace their free space mass with the effective mass of that material, in that material. So we can forget about all the periodic potential of the lattice and consider the effect of only any externally applied electric field or magnetic field. So this truly helps one to perform device analysis with a minimal use of quantum mechanics. So this effective mass approximation, okay, so this is an approximation, so we should know what's the validity of this approximation. So this effective mass approximation holds true as long as the carriers, okay, they are either very close to the bottom of the conduction band or at the top of the valence band, all right? And also similarly, whether we can approximate the bottom of the conduction band or the top of the valence band as a parabola. So this is known as a parabolic approximation. That is because if you try to calculate the curvature of a parabola, it's a constant, right? And also there should not be a multiple bands. Okay, then there are some cases known as degeneracy where there are multiple bands at the same energy level and there could be tight coupling between these multiple bands. Okay, that typically happens in the case of whole energy bands. Okay, so as long as you have to make sure that these conditions are valid, then you are good to go with effective mass approximation. But the price one has to pay for this approximation is that you may have to live with different effective masses for different phenomena, right? So in the first tutorial, we saw that there was a problem to calculate the electron concentration in conduction band and similarly hole concentration in valence band, right? So we have used a density of states expression to calculate it. So the effective mass, okay, effective mass used in the density of states expression is known as density of states effective mass, right? So that is not truly the curvature of this EK diagram, right? Although this density of states effective mass, it's a function of this effective mass, the band structure effective mass, right? And that formula is not, okay, you cannot apply a single density of states effective mass, right, for all the materials. So actually this similarly that's a true in the case of if you want to calculate the conductivity or mobility, there also you have to put in some effective mass. So these all the other effective masses, they can be written as some kind of an average. Okay, so here by average I don't mean arithmetic mean, right? So some kind of an average of the band structure effective masses. So in summary, effective mass is a quite useful approximation, right? As it enables an electrical engineer not to bother about quantum mechanics and perform device analysis with semi-classical physics. So in this slide, we will compare the properties of a missing electron near the top of a valence band and a hole at the same location. So the missing electron, it had a negative charge. While we saw that, okay, if you want to get the same dynamics, okay, if you want to place a hole at that location, okay, we have to treat it as a positively charged quantity. Typically we take the top of the valence band as 0 electron volt, right? So any electron which is below the top of the valence band, okay, so their energy will be considered as negative, right? So, but the whole energy band diagram, for the energy of the hole, actually it increases downward in the EK plot. So any hole which is below the top of the valence band, okay, they have positive energy. So if the wave number of the missing electron is Ke, right? So then the wave number of the hole at that location is actually minus Ke. So the group velocity, we saw that the group velocity is defined as the 1 over h cut into dE by dk, right? Suppose the group velocity of the missing electron was Ve, right? The group velocity of the hole at the same location is same as that of a missing electron. That is because when you take the derivative, the numerator and the denominator, the sign is flipped, right? The energy is also different. The k vector is also as a sign change. So that is why the group velocity sign remains the same. However, for the effective mass, we saw that near the top of the valence band, the curvature is negative. So the electrons in that valence band, okay, they have a negative effective mass, right? But for the holes, okay, so we have to consider them as positive effective mass, because if you try to calculate the curvature of the whole bands, okay, that is actually positive because the energy increases downward. So as long as holes remain in valence band, or if they move from valence band of one material to the valence band of another material, right, we cannot distinguish between the effect of valence band electrons and holes, right? So any experiment, okay, if you okay, they will give you identical results, right? So holes are really quasi particles, right? So later in solid state physics, okay, you may encounter other quasi particles like plasmons, polarions, etc. But the valence band electrons, they are real. Actually, for example, you can emit the valence band electrons out of the valence band into vacuum, right? But you cannot emit a hole from a valence band into vacuum, right? Now, let me come to the last topic of the discussion, that is Fermi level. So we have encountered Fermi level first while discussing Fermi-Dirac statistic to calculate the occupation probability of an energy state. So if you are given a system of free electrons with chemical potential mu, then the probability of a state with energy E to be occupied is f of E is equal to 1 plus this expression, right? I'm sure you have seen this expression for the Fermi-Dirac statistics, right? Well, the only difference is that you might have encountered instead of mu some symbol like EF, right? Now let's see what is chemical potential. Chemical potential is the change in Gibbs free energy when a particle is added or removed from the system. So the Gibbs free energy is the amount of available work you can take out from the system. So strictly speaking, Fermi level or Fermi energy, right? It is the chemical potential at a temperature T is equal to 0 Kelvin, right? Sometimes Fermi energy or Fermi level is also defined as the energy of the topmost occupied electron state. However, this definition works for metals because for metals the conduction band is partially filled, right? And then you can define you have states which are occupied all the way up to the Fermi level in metals. So this definition actually often creates confusion among students when we try to derive the position of EF at 0 Kelvin for an intrinsic semiconductor. So this definition actually it's not true for semiconductors or quantum wells with the discrete energy states. So for such systems, actually the Fermi level, right, at 0 Kelvin, it lies halfway between the highest occupied energy level, right, and the lowest unoccupied energy level. So you may recall that for an intrinsic semiconductor at 0 Kelvin, the Fermi level is given by EC, that is the bottom of the conduction band, plus the top of the valence band by 2, right? So Fermi level lies at a place where there are no energy states. So here is something you can think over, like find the position of Fermi level in an N-type or a P-type semiconductor at 0 Kelvin. So in semiconductor literature and textbooks, right, solid state devices textbooks, the Fermi level actually means, okay, so they violate this strict definition. So Fermi level means the chemical potential of the electron at any temperature, right? So that is why in our textbooks and classes, in the expression of the Fermi occupation factor here, right, we typically use EF instead of mu. Now let us see the importance of this Fermi level chemical potential. So for a device with many terminals, right, the chemical potential mu at any terminal, it can be raised or lowered by the application of a voltage. So if you apply a positive voltage to at any lead, right, on a terminal, right, the chemical potential there gets lowered. Similarly, if you apply a negative bias, the chemical potential there gets raised. Similarly, suppose if you connect a voltmeter between two terminals of a device, right, the in reality the voltmeter measures the difference between the levels of chemical potential between at those leads, right? So for example, the potential between these two leads, right, at point A and point B is nothing but the difference in the chemical potentials, right, divided by the electronic charge. So later, when you study more about semiconductor devices like a PN junction, right, you can then wonder what a voltmeter would measure when connected across a diode at equilibrium. So these are two very good reference books. They are just around 250 pages. This first book, in its totality, the entire contents of the first book is very valuable for an electrical engineer who wants to know more about the physics of solid state devices. Similarly, these books, okay, some of these chapters, okay, excluding areas like magnetism or superconductivity, they are quite good for this topic. Thank you.